is an interactive projection for aerial dance using depth sensing cameras. Welcome.
Thank you, everybody. As said, my name is Zuzor, and this was a joint work with Zachary Seldes and Shlomo at the College 2 at UCC. So what we're going to be talking about today is Zuzor, which is what we like to call our system. The components, how everything works, different application areas that we thought of, and creative thinking behind the projection and how we use the system. And we're going to have a little video demo at the end. So Zuzor, what it is, it's an interactive performance system for floor and aerial dance. Controls visual and sonic aspects of the presentation using the Microsoft Kinect. What aerial dance is dance with aerial apparatuses, which is commonly known as trapeze, silks, and often seen in Cirque du Soleil and other cirque shows. What our system does is detects free movements in space with 3 degrees of freedom. It can measure and track movements, and it has some gesture recognition and tracking capabilities using a simplified hidden markup model. And additional video effects can be used by using depth and other aspects given from the Kinect. This is used to create like an overall augmented reality for the performances and create a new performance stage of performance. So the component, there's the Kinect, which you can see here. There's also an infrared camera tracker software that we developed. There's a gesture recognition software, graphic animation, projector, and finally the performer with the infrared marker that we use. This is a little picture to show it all connects. First, the Kinect connects to the computer. It has all these softwares running, connecting back to the projector and projecting onto the performer. All on like live during performance and getting feedback from the performer and adjusting. So the Kinect, this is commonly known for its use in Xbox, developed by Microsoft. What it has an RGB camera, has a depth sensor, and the depth sensor uses an infrared projection and a monochrome CMOS sensor to generate a 3D image of the space. Since it has the infrared projector, it can work regardless of the lighting in the room. It also has a multi-array microphone, but that's not used in the project currently. And finally, it can stream either the RGB image or the infrared image to the computer. So we only use the infrared image. So this is the user interface for the tracking system. This receives the infrared image, as I said, receives a depth image. It does not detect the RGB because we have to prioritize the infrared over it. It has other nice little options like camera tilt, can record the depth and infrared images, information, and for the infrared, you can create a threshold. So in a room where there are multiple infrared sources, you can set the threshold high enough that only your marker is visible. Other than that, it also has the cool settings, which is just an extra nice feature that can create a very specific index for X, Y, and Z coordinates. So in a wide room like this, we could block off the walls and we can control what depth it actually looks for. So the pre-custom 3D coordinates of blobs. So for our infrared marker, we have infrared tape that we use. And we just hook it onto the performer. So what it does is it gets the raw data from the Kinect. It converts the raw depth value into meters. And then it gets all the different infrared images, and depending on the threshold, which is user defined, depending on the space, it adjusts to take only the brightest one, or whatever you choose to be above the threshold. And then it segments the 2D blob. And basically, that means it creates a border along the blob. So in an infrared marker like this, you just get the outline. And from that, it gets a depth estimate by averaging all the depth values it gets. And finally, when you have your specific chosen infrared markers that it tracks, it only then captures the X, Y coordinates. Here we have a little video. This is me doing a back walkover with the infrared marker attached to my ankle, and this is what the depth view looks like. So you can see the green square around the infrared marker. And here again is the user interface, and our threshold in this case was only 0.5. And the way that we can tell the view and the depth view, is by the grayscale. So the lighter it is, the closer it is to the connect, and the back wall is grayer since it's farther back. Now, this is the infrared view of what the Kinect sees. So again, you see here the infrared marker and how it's very brightly shown. There's also, I don't know how well you can make, but there's a very specific infrared sequence that the Kinect uses to, there's an infrared projection onto the wall and onto me. That's very specific to every Kinect that it uses to make out the depth. But since our threshold is high enough, it only follows our marker. And the gesture recognition software. So the way we identify gesture is by representing the sequence of the XYZ coordinates of the marker as it moves through space. Unfortunately, it's a bit unforgiving. So if you have two gestures in which one I move my right arm, the other one I move my right leg and right arm, it would see it the same, it's only tracking the infrared and not my leg. The way it works is as a recognition and tracking using modified and markup model, which connected its overall likelihood and time index and detected speed compared to your recorded gesture and your executed gesture. So again, if the gesture is just me moving my arm to the right, it can track it and identify it compared to other gestures we have recorded. And it can also tell you how fast it is compared to the initial recorded gesture. In markup model, observation probabilities are set by the user. So talking a little bit about the markup model, it creates a left to right Cartesian chain. So as you can see here, for this given gesture, it has the X value that it records, the corresponding Y value, and the corresponding Z value. From here, every instance corresponds to a state. So we have this state, this state, this state. And then the probability of the observation is represented by a normal distribution. So compared to your initial recorded gesture, it has a little normal distribution, and if it's within a certain probability, it accepts it and recognizes the likelihood. For detected speed, as it jumps from state to state, it has the option of staying in the same state, which means you're not moving fast enough, you're moving less than the recorded speed of the rehearsed gesture. It has, you can just move straight forward, which means 1 to 1, or you can move 2. So again, if I record moving the infrared marker from left to right for me, moving it slowly, it would stay on one state and then jump slowly, which would be less than the one speed, relative speed. If you move it at the same speed, it would just jump state to state and give you 1. And if you go faster, it would skip to try and keep up. So the fastest speed it can detect is 2 times the recorded speed gesture. Here's a little insight into the code. This is a little technical on just the way everything works, but here you can see this is the recorded gesture. Again, X, Y, and Z coordinates of the gesture. Here we have the depth image that we see, and this is the infrared marker, again visible, user interface. And here I think our threshold was 0.8 because of the background there were some reflections of the sun. Here you can see the likelihood. So we had 5 gestures recorded. They were all different aerial drops. And from that, it calculated the one with the highest likelihood and outputs that as its current gesture. again, it can detect the speed and the time index. So the time index meaning it can detect where in the recorded gesture you are. Here, this was a different iteration for the same test. Of course, it didn't have quite as easy a time recognizing this one, and detected speed is kind of all over the place as trying to see which gesture it was. So animations. We currently use the Quartz Composer to construct animation. Quartz Composer is a node-based visual programming language that comes on a Mac. We have it communicating with the infrared marker tracking and gesture recognition using OSC over EVP. OSC being open sound control. You can use your datagram protocol. So basically, we have the XYZ coordinates and the gesture recognition information feed into the Quartz Composer, and from their control react with our desired animation. Setup. Again, so we first place the infrared marker on the performer. So again, this would just be hooking this wherever you want or attaching it to a costume. You then connect and project to the computer, like so. And you bind the ports appropriately so that everything communicates correctly. So application areas, what we thought of that could be useful for performances in interactive augmented reality was applying it to dance. We actually have a little demo that shows this later on, but we have so basically, instead of it just being a solo with no background or anything, or with sort of main background, you can actually have kind of a partner piece with the animations. So it's between the dancer and the reacting animation and interacting and whatever you program. We thought of circus, so again, like Cirque du Soleil. For aerial jobs, we were going to use like graphic emphasis on tricks. So as you do a very intricate trick, you could record it as a gesture and then recognize it live, and from that have certain animations correspond to it. Lastly, theater. This one is kind of not as fancy, but we just thought of like a spotlight tracking the actor on stage by just having an infrared marker either on him or somewhere in his costume. So instead of manually moving around a spotlight, you could just place that on him and our software will just track it. And if you have any ideas for further application areas, please let me know. We'd love to hear it. So creative thinking. This is where more of like the artistic side comes in. So I'm studying math, computer science, and dance at UC Berkeley right now. And this is where like the creative aspect kind of leads through. So here for each performance, we need to try and create a personalized interaction and augmented reality for that specific performance. So what we thought of is a direct mapping, which means that again, you just hook infrared and then you feed it the exact X, Y, Z coordinates and have the corresponding visual effects. So a common one is just having like a colorful circle follow the arm, project onto you as you dance. Or any show you're doing, it doesn't have to be dance. The gesture following. So what that would mean is if you record a circle during your rehearsal space, then you record a circle in your arm, then again, on stage you could circle your arm and that would create and trigger a certain animation. So again, this is very free and you can play with it as you like for your certain performance. And then event detection, basically within a gesture, we can place markers throughout the index, the time index. So it can detect not only when you finish the gesture, but also halfway through, a quarter way through, and so on, if you'd like to have a very controlled animation. Lastly is actor immersion. This actually doesn't use infrared. What we thought was just depth segmentation. So basically using the Connect, we can only look at a certain depth value, which would be the performer, so then you could ignore all background objects, and from that create kind of a live silhouette of the performer. So now